Chapter 28, Direct Current Circuits. We studied two elements in a typical electrical circuit. One is a capacitor, and the other one is the resistor that we studied in the previous chapter. So now it is time for us to put together these elements in a real electrical circuit. In particular, the type of circuit we study in this chapter is a so-called DC or direct current circuit. As you probably know, there exists another type called AC circuit or alternating current circuit. What is the difference between these two types of circuits? In a DC circuit, the direction of the current flow, like in this particular case, is always clockwise or always counterclockwise. It does not change over time, even though the magnitude of the current may change over time. In an AC circuit, the direction of the current changes back and forth all the time. We're going to study DC circuit first in this chapter and AC in a later chapter when we deal with the magnetic field, because it turns out as you reverse the direction of the current, you have to deal with the magnetic behavior, not just the electrical behavior of a circuit. So let's focus on a DC circuit first. We are going to first make an analogy between an electrical circuit and an artificial waterfall. You know, there is a lot of similarities between gravitational case and electrical case. In a gravitational case, you have the gravitational potential energy, which gets higher as the elevation gets higher. In the electrical case, you have electrical potential, which also has different magnitudes depending on the voltage, not depending on the heights. But there is a lot of similarity. In the case of an artificial waterfall, it's not a natural waterfall where you got rainfall coming from the top of the mountain and or snow melts or whatever. It gradually cascades down to a lower elevation, powered by the gravitational force. In an artificially sustained waterfall, you have a finite amount of water, okay, and this water is pumped to a higher level by an electrical pump, which turns electrical energy into gravitational potential energy. So as the water gets to a higher elevation, it then flows downwards, it loses gravitational potential energy, and then it has to be pumped back up again so that the cycle can start. So this is how to sustain an artificial waterfall. You need a pump, okay, which increases the potential energy, the gravitational potential energy, so the cycle can start over again. And ideally, if this flow cycle has no friction involved whatsoever, then would you still need such a pump? Well, imagine, let's say a little water drop. It falls downwards without any friction, okay, without any viscosity. So as it falls, it's going to lose potential energy, but it's gained kinetic energy by the same amount, right? So it will be accelerated as it goes downwards, and it can go back up by itself, losing kinetic energy, but gaining all the potential energy back. So it will sustain itself. You wouldn't need a pump. But of course, that is under an ideal circumstance of a frictionless world. In reality, you always have friction, and therefore you do not get all the kinetic energy in return for the potential energy you lost, and therefore you need a pump to push the water back to the same level. The same thing goes for an electrical circuit. We have here the simplest possible version of the electrical circuit diagram. We use symbols instead of realistic drawings for the elements. You have a battery and you have a resistor. These are just metal wires. Okay, now the battery, just like the pump, is what it takes to sustain the current flow. Okay, to sustain the current flow. So what happens is that electrical current flows from the positive terminal of the battery, where the potential is higher, from the lower or negative terminal of the battery, where the potential energy is lower. So the current flows like that. Okay, so imagine positive charges flowing from here to there. So you have here a higher potential, here a lower potential. It flows through the resistor, and as it flows through the resistor, it loses electrical potential energy, right? Because it went from higher to lower potential. But what happens in return? Well, in return is that the potential energy, electrical potential energy lost, is turned into heat as these particles, as these charge carriers collide with the particles in the resistor. causing the resistor to heat up. So basically, there's a transfer of electrical potential energy into thermal energy. That's why the resistor will heat up. So they lose this energy, so they have to be re-energized. And how does that happen? Well, once you're here, you're in a lower potential spot, but the battery will then pump you up. So as you move across the battery, the potential energy gets higher again because the battery lifts you up to give you more potential energy. It's very much like a pump. As the water flows downwards, it needs to be lifted back up to a higher spot, gaining the lost gravitational potential energy back. Okay, so this pump and the battery, they're analogous to each other, and the water flow here is what? Is analogous to what? To the current flow here. Okay, and then again, if there were no resistance, then that means there is no mechanism to turn the electrical potential energy into heat. Okay, then would you still need a battery? No, it's just like here in an actual frictionless situation, you wouldn't need a pump. It just goes back and forth, goes on and on by itself. Okay, but in reality, because there's always some resistance in a real circuit of resistance R, you would always need a battery, which provides the lift in potential. So this is the basic analogy between a mechanical system and an electrical circuit. Now take a close look at the battery. What's going on there? Let's see. As a certain amount of charge dq, which you assume to be positive, goes from the negative to the positive end of the battery. Okay, the battery does some work to it, does some positive work to it, therefore increasing its electrical potential energy. It's just like a pump lifting a water drop from lower to a higher elevation, increasing its gravitational potential energy. The pump has to do positive work to it, right? Here is the battery that does positive work. Okay, so how much work is done by that battery in lifting this much charge from here to there? Well, the amount of work done, of course, is proportional to dq. Okay, it is also proportional to a constant, which is a characteristics of the battery. We call it epsilon. So epsilon is dw over dq. We call epsilon EMF. Okay, epsilon is called EMF. It's a short for electromotive force. I put a quotation mark for this term force because it is not the real force. Okay, it's not measured in newtons. What is EMF measured in? SI units. Well, it is joule per coulomb. Now, as you recall, this in fact is the same as the unit of volt, which is that for potential, electrical potential. Okay, so what is epsilon anyway? By definition of potential difference, as you move a charge Q over potential difference delta V, okay, against the electric field, then there is an increase in energy. There is an increase in energy, electrical potential energy for this amount of charge. Okay, for this amount of charge, delta V, and that requires a work. It requires some work to be done. Okay, on that charge to increase its the potential energy. So that is dUE. That's how delta V is related to dUE. Okay, here delta V is the increase in the potential. Okay, for that particle as it moves from one place to another. And dUE, actually delta UE, or let's call it dV. Okay, dUE would be the increase in the electrical potential energy. If you compare these two, okay, if you compare these two, and you notice that the work done by the battery becomes the increase in the electrical potential energy of the charge, right? Then what you have here, dV, and what you have there, epsilon, they actually correspond to each other. What does that mean? It means epsilon really is just a potential difference, okay, between this terminal and that terminal. I'm assuming that this is an ideal battery with no internal resistance. In other words, all the work done by this battery as it lifts a certain amount of charge from here to there is used exclusively to increase the potential energy of the charge. Nothing is wasted to overcome heat, for example. In other words, to overcome an internal resistance. If that were the case, then you have dW equals epsilon dq, and this epsilon is really the potential difference, okay, between the negative and the positive terminal. It's just like the water pump providing a height difference for a water drop between the starting point and the ending point. It lifts it up through that potential through that height difference, therefore increasing its potential energy. Okay, and obviously you need an EMF to sustain a current, and the greater the value of epsilon, the greater the potential energy gained by a certain charge flowing from here to there, and the stronger the current will be in the circuit. Okay, now a real EMF, a real battery, always has a little bit of internal resistance, so as the charge flows from here to there, only part of the work done by the battery is actually used to increase the potential energy of the charge. Another part has to be used to overcome the heat, okay, to pay for the heat that is generated as the charge makes its way from here to there, and that is caused by the internal resistance. So we have here a simplest possible real circuit, not an ideal one, but a real circuit. What you have is, of course, a battery. You need a battery, okay, and this battery has an internal resistance, because all real batteries do, which we call small r. Okay, so in this silver box is the complete battery, which includes an EMF and an internal resistance. Okay, now let's see what happens. We'll hook up this battery to a load which means an external resistance. It can be a light bulb, can be whatever it is. Okay, and then you can sustain a current like this. Let's take a look at what kind of current is going to be produced by this battery. First of all, current flows from positive to the negative terminal of the battery. So in this case, it is flowing clockwise. Okay, clockwise. Now, I want to know what happens to the electrical potential going from point A to point B to point C to point D. Okay, this will allow me to figure out the current. First of all, let's start from point A. Okay, now you can always define a reference point or a 0 point of the potential, electrical potential, at any point you want. This point is connected to the negative terminal of the battery, and by convention, we usually call this zero potential. You don't have to, but we usually call it zero potential. So VA is equal to 0. Okay, 0. Now, imagine you go from here to there. As that happens, what happens to the potential? Well, the potential will get higher because there's a potential difference between point A, which is negative terminal, and that point, which is positive terminal, right? How much is the potential difference? What is epsilon? Okay, it's epsilon. So once you reach that point, the potential becomes epsilon. That will let you reach this point, and from that point you have to go through an internal resistance. Now, anytime you flow through a resistance, you have to pay a price. You have to decrease your electrical potential energy. Why? Because you have to use part of that energy to pay for the thermal energy, for the heat that is generated. Right? So, and that is Ohm's law. So the potential is going to decrease, okay? You know, so because the current flows from higher to lower potential. You have to decrease potential. How much is potential decreased? By Ohm's law, IR. So the potential goes down by I times R, and that's a negative sign because the potential goes down. Okay, this gets you to point B. Now, once you're in point B, you flow to point C. They have the same potential because I'm assuming the wire has no resistance. This will get you to this end of the load, which has a higher potential than that end. Why? Because the current flows always from positive to negative terminal of the resistor. As it flows, the potential decreases by how much? Well, again, it's from Ohm's law, so minus what? I times big R, right? This will get you to point D. Now, point D and point A, they have the same exact what? Same exact potential. So what was the potential at point A? It was called 0, so this is also 0. That's the potential at point D. Okay, so really this is VA. This is VA. VA equals 0. And that is VD. Okay? And they're the same. So it tells us that epsilon minus IR minus I big R equals 0. So therefore we say epsilon equals I times small r plus big R. In other words, the current in the circuit is epsilon divided by big R plus small r. Okay, this is really simple in terms of calculation. It's our simplest possible circuit, but you can see this is the idea how we get the current in the circuit based on the EMF or the battery installed and based on the total resistance, which in this case is big R plus small r. Okay, it is easy to understand qualitatively why the total resistance is the sum of these two, because the current has to flow through both of them, and as it flows through each of them, it has to pay a price, it has to generate some heat, so you have to add the two resistance up. It makes sense. Okay, so this is the current. Now, suppose I want to, suppose this is a light bulb, okay, and I hook up to a battery. Now, if my job is to make sure the light bulb is as bright as it can be, okay, how do you know what does it take for the light bulb to be really bright? That means a lot of energy in heat and light are released, right? And that means you want the greatest power consumption on the load, which in this case is a light bulb. Okay, how much is the power converted from electrical form to thermal form on this? Well, we learned it is I squared times R, right? That's P R. That is the power consumed by the load. If I want a light bulb to glow as bright as possible, I want to maximize this. Okay, I want to maximize this. Now, suppose you hook up to a battery of given EMF. Okay, so epsilon cannot change. Of course, otherwise you can always increase epsilon, you can increase P, right? But suppose epsilon cannot change. However, I'm allowed to change the resistance of the load or of the light bulb. You know, you cannot change small r because that's part of the battery, but you can change the load. Is it possible for me to adjust this load, big R, such that you get the greatest power consumption? You draw the greatest power, in other words, from this battery. Okay. How can that happen? Well, right now, I have R. I is a function of R, right? You can see from here, I is a function of R. So what I need to do is I need to optimize the value of big R to make P the greatest. Before I can do that, I must rewrite the current I as a function of big R. So I can write this as epsilon over the sum squared times R. And then we can write this epsilon squared, okay, which is a constant, big R over big R plus small r squared. Okay, this is a function of R, of course. Okay, it's a function of R. Small r is fixed, epsilon is fixed, but as big R changes, P will change. Now we can do a little plot of this function this is a function of R. You can have a rough idea what happens. Okay, here is P as a function of R, right? And let's say this is R. Now R can be as small as 0, can be large as infinity. Okay, if this R is 0, then of course there's no current, there is no potential difference between point C and D, and therefore there is no heat generated. Okay, R is 0, right? So P will be 0 here. On the other hand, if R goes to infinity, okay, if R goes to infinity, what happens to the power? Well, if R goes to infinity, no current can flow whatsoever. I will be 0, so would be P. So you got a 0 here and 0 there, right? It's 0 at both extreme ends. But on the other hand, in the middle, when big R is neither 0 nor infinity, you know, you have to have a finite power consumption, right? So obviously, it has to rise, and then it has to fall back to 0. It's something like that. Okay. Now the details of this curve is described here, but you can see here, at some point, for an optimum value, there will be a maximum output of power. So this is the optimum value of the load, which draws the greatest amount of power from the battery. The question is, what is that equal to? Okay, can we figure that out? Well, it's a single function variable. How do we find the particular value of R which makes this function the greatest? Well, you know how we do that in calculus. Set df dr equal to 0, okay, and that will give you the optimum value. Okay, that will give you the optimum value, and it's quite simple to do. And it turns out when you do that, you find, interestingly enough, big R equals small r. Okay, so all you need to do really is to install a light bulb which has the same exact electrical resistance as the internal resistance of the battery, and that light bulb will grow brighter than any other light bulb with any other value of resistance. And this procedure of optimizing the load to draw the greatest power from the battery is called load matching or resistance matching. So this is a interesting way to analyze this very simple circuit to see how we can draw the greatest power.